Hello, good afternoon. My name is Vanessa Santos and my project will be on complex numbers. Here is a quick outline. We'll be going over the introduction, properties of the square root of negative numbers, the power of I, what is complex number. We'll be talking about the properties, how to add complex numbers, how to subtract, multiply, and divide. And then we'll be at the end talking about the Euler's formula. So this is a quick background. Carl Gauss provided that every polynomial square of degree n has exactly n roots. Gauss discovered comes from the fundamental theorem of algebra. This theorem states that within complex number systems, every polynomial has a root. In other words, once we introduce the I, that's not only we can solve the equation x squared plus 1 equals to 0. We can solve all polynomial equations. And then we also have Del Ferre contribute to this complex number by trying to find a formula like the quadratic formula for equations with the highest power of the 3 cubes. The quadratic formula is super useful because it gives us the roots of any equations with the highest power of 2. Del Ferro first considered that the case where the x squared term is missing and the last term is negative the last term is negative. In the 16th century, negative terms were way too sketchy to write, so Del Ferro wrote his cubes as x cubed plus cx equals d, as required c and d to be positive. The problem here is to get x by itself on one side and all of the constants on the other side. Del Ferro was trying to do the same thing for his cubic equations, and throughout some clever substitution, he eventually found the solution, just like the quadratic formula. Del Ferro's new formula allowed him to find the solution to the cubic equation by simply plugging in the values. After Del Ferro, of course, there were so many more mathematicians, and Euler is one of the ones that we can relate with the complex numbers. Leonardo Euler came up with the Euler's formula. Okay, so this is what a complex number is. A number that consists of two parts, one real, one imaginary. For real numbers a and b, the number a plus bi is a complex number. If b is 0, the complex number reduces to a which is a pure real number. If a is 0, the complex number reduces to bi, which is pure imaginary number. In other words, all numbers, real and imaginary, are in the set of the complex number. The way you write a complex number is a plus bi, which be a and b being real numbers and I being the imaginary. The properties of the square root of a negative number. If r is a positive real number, then the square root of negative r equals to I to the square root of r. These are a few examples. The square root of a negative 3 equals to I, which is negative square root of 3, I'm sorry. And the square root of negative 4 equals to I to the square root of 4, with the square root of 4 is 2, which equals to 2I. Then the power of I. If I is equal to the square root of a negative 1, then I squared is equal to negative 1, I cubed is equal to negative I to the fourth power is equal to 1, I to the fifth power is equal to I to the sixth is equal to negative 1, I to the seventh power is equal to negative and I to the 8 is equal to 1, and edit. And a quick way to prove this is if n is eventually divisible by 4, then I to the square root of n is equal to 1. If the remainder is 1, then I to the square root of n is equal to I. If the remainder is 2, then the square root of the I to the square I to the power n is equal to negative 1. If the remainder is 3, then I to the square root of n is equal to negative I. These are a few examples of complex numbers. All numbers can be expressed as complex numbers, which will be 3 plus 0i, and negative 6i is equal to 0 minus 6i. Two complex numbers of a plus bi and c plus di are equal if a equals to c and b is equal to d, which are the real numbers. These are the properties that are used in order for us to solve complex numbers. We'll be using the associativity property for addition and multiplication, which is x plus y equals to, x plus y plus z is equals to x plus y plus z for our real numbers in x and y and z. And x times y times z is equal to x times y times z for our real numbers x and y and z. The commutative property for addition and multiplication, it will be x plus y is equal to y plus x for our real numbers x and y and z. And x times y equals to y times x for our real numbers x, y, and z. The distribution property for multiplication over addition reads as x plus y times z, which equals to x times z plus y times z for our real numbers of x, y, and z. Okay, and then here will be an example of how we will be adding complex numbers. The way we add complex numbers, I believe is the most simple, simple one, because it gets pretty complicated when we get to division. But for adding complex numbers, what you do, you go ahead and add the like terms. So if we add, if we have 8 plus 7i plus 4 plus 3i, we combine like terms. So we'll be adding 8 plus 4 plus 7i plus 3i, and then we'll get the 12 plus 10i. For subtraction is almost the same thing. All we need to do is make sure that we distribute the negative into the minus sign into the equation, which will be 7 plus 9i minus 3 plus 4i will equal to 7 plus 9i minus 3 minus 4i, which then we combine like terms, which will be 7 minus 3 plus 9i minus 4i, which gives us 4 plus 5i. Remember that I will be equal to the square root of -1. And for multiplication, what we go ahead and do, we do the FOIL method. When we do the FOIL method, we get an equation 3 plus 2i minus 4 times 4 plus 5i. Doing the FOIL method, we get 12 plus 15i plus 8i plus 10i squared, which equals to 12 plus 15i plus 8i minus 10, being reason that I squared is going to be equal to -1. So then we equal that to 2 plus 23i. And then this is where it gets a little complicated, when we divide the complex numbers. If we divide 6 plus 3i divided by 5 plus 2i, we're going to be getting 6 plus 3i over 5 plus 2i times 5 minus 2i divided by 5 minus 2i. And then we get the 30 minus 12i plus 15i minus 6i squared, all divided by 25 minus 10i plus 10i minus 4i squared. Remember that the I squared is equal to the -1, so then we get 30 minus 12i plus 15i minus 6 times -1 all over 25 minus 10i plus 10i minus 4 times -1, which gives us 30 plus 3i plus 6 all divided by 25 plus I, which equals to 36 plus 3i over 29. Now the Euler formula, that one is the way we get to polar, that way we can graph it on a polar equation. So he was able to determine that the e to the power of I data is equal to cosine data plus I sine data. When x is equal to -2 plus 3i, which that will x is equal to a plus bi, which is equal to r e to the power of I data, r equal to the absolute value of x, which equals to the square root of a squared plus b squared. So then we just plug in the a and the b, which be -2 plus 3 and the 3. So -2 squared plus 3 squared will give you 4 plus 9, and of course square root of 4 plus 9, which you get you a square root of 13. So remember that a plus bi is equal to the r cosine data plus I r sine data, which tan data is equal to sine data over cosine data, which equals to b over a, which equals to -3 over 2, where data can equal to the tan inverse of -3 over 2. And here's an example of how we would graph this on a polar polar coordinates. Remember that it's the imaginary line over real numbers. So the imaginary line is in another dimension. It's not just simply of an x of a x and y. So imaginary numbers are graphed using complex numbers. Okay, and these numbers or complex numbers are used in electromagnetics. That's the way we can go ahead and solve those problems. So complex numbers are used in real life. And that concludes my presentation.